Imagine sitting inside a 5-ton block of steel and high-tech avionics that by all rights should stay firmly on the ground. It doesn't have wings to glide, and it doesn't have a jet to blast it forward. Yet it sits there, hovering in a way that defies every intuition you have about flight. You probably think flying a helicopter is like driving a car in the sky. It isn't. It's more like trying to balance on a unicycle while standing on a beach ball in a hurricane. Physics is actively trying to tear this machine apart every second it's in the air. Today, we're going to pull back the curtain on the most complex mechanical system ever mass-produced. We'll see why your brain is lying to you about how they steer, why military pilots have to learn to see two different things with each eye simultaneously, and how these devil's chariots can keep flying even after the engine dies. Let's start with a problem. You have a massive main rotor on top. The engine turns that rotor. Simple, right? But here is where Sir Isaac Newton enters the chat with his third law: action and reaction. If the engine turns the rotor to the right, the helicopter's body wants to spin to the left with equal and opposite violence. Without a solution, the cockpit becomes a high-speed centrifuge. Now you're thinking, that's why we have that little fan on the tail. And you're right. But it's not just a fan, it's actually a tiny helicopter turned on its side. Its only job is to push against that spinning force. But wait, if you add more power to the main rotor to climb, the spin force increases. Therefore, you must also change the tail rotor's thrust at the exact same moment. If you don't, you start pirouetting across the battlefield. Some modern helicopters, like those with fenestron systems, hide this rotor inside a tube for safety and noise reduction, but the principle remains. Every time a pilot moves their hands, their feet have to dance on the pedals to keep the nose pointed where they want. It's a constant 4-limb aerobic workout just to stay still.
Now, stop. You might think, okay, that's just basic talk. Give me the hard stuff. Well, pull up a chair and grab an espresso, because we're about to talk about why the helicopter steers exactly 90 degrees away from where you tell it to.
The main rotor isn't just a propeller, it's a massive, heavy gyroscope. And gyroscopes have a nasty habit called precession. If you push a spinning disc at the 12 o'clock position, the effect doesn't happen at 12. It happens 90 degrees later at 3 o'clock. Therefore, if a pilot wants the helicopter to tilt forward, the mechanical system has to change the blade angle while the blade is still off to the side. This is handled by the Swashplate. It's one of the most complex mechanical parts ever built. It takes the pilot's simple request, "go forward," and translates it into a synchronized dance, where each blade changes its pitch angle multiple times per second as it spins. It's a mechanical computer that has to be perfect, or the vibrations will literally shake the bolts out of the airframe. But it gets worse. When you start moving forward at 150 knots, approximately 280 kilometers per hour, the blade moving forward has its speed added to the helicopter speed. The blade moving backward has the speed subtracted. This means the forward side creates massive lift, and the backward side creates almost none. This is dissymmetry of lift. Without a clever fix, the helicopter would roll over and crash the moment it tried to fly fast. The solution? Flapping. The blades are allowed to hinge up and down. The blade with too much lift wings up, which actually reduces its angle of attack and lowers the lift. The weak side drops down, increasing its angle and gaining lift. The rotor literally breathes to stay level. It's a self-correcting mechanical miracle.
Are you still with me? Because if you think the physics is a headache, wait until you see how a military pilot actually sees the world. They aren't looking through a windshield. They're living in a video game that can kill them.
Meet the AH-64D Apache pilot. They wear a helmet called IHADSS. Over their right eye sits a tiny glass monocle that projects thermal imagery, flight data, and targeting reticles. Their left eye? It's just looking at the dark cockpit. The human brain wasn't designed to merge these two images, but military pilots have to train their brains to process them independently. Here's the dirty secret. The nose-mounted thermal camera, the TADS/PNVS, is slave-linked to the pilot's helmet. Wherever the pilot looks, the camera looks. If the pilot looks 90 degrees to the left, the gun and the sensors snap to that position instantly. They are literally looking through the floor of the helicopter using infrared sensors. They don't see the air, they see the heat signatures of engines and bodies through miles of dust and smoke. Modern machines like the Viper and Venom have replaced steam gauges, old dials, with a glass cockpit. Massive LCD screens that consolidate thousands of data points into simple symbols. They have moving maps, threat footprints, and target handovers where one helicopter can see a tank, press a button, and send that data to another helicopter miles away. It's an airborne local area network for war. And then there's the firepower. We're talking about Hellfire missiles for tanks, 70mm Hydra rockets for area suppression, and 20mm cannons that spit out hundreds of rounds per minute. But it's not just point and shoot. The pilot has to manage weapon zones, laser codes, and engagement areas, all through their digital menus while flying 10 feet, approximately 3 meters off the ground to avoid radar. The AH-64D Apache Longbow has a distinct mushroom on top of its rotor. That's the fire control radar. It allows the helicopter to stay completely hidden behind a hill or a tree line, pop only the radar up, scan 128 targets in seconds, prioritize the most dangerous ones, and then pop up for only a few seconds to ripple fire missiles. It's a ghost with a sledgehammer. But what if the engine fails? In a plane, you're a glider. In a car, you're a brick. In a helicopter, you become a wind turbine. This is called autorotation. As the helicopter falls, the air rushing up through the blades spins them faster. The pilot changes the blade angle to store that spinning energy. At the very last second, just before hitting the ground, they flare, using that stored energy to create a sudden burst of lift for a soft, engine-free landing. A military helicopter is a machine built on 1,000 contradictions. It wants to spin, but we force it to stay straight. It wants to fall, but we teach it to use gravity to save itself. It isn't just a vehicle, it is a supreme act of human will imposed upon the laws of physics. Next time you see one, don't just see a noisy machine, see a masterpiece of controlled chaos. If you learned something new about how these metal beasts stay airborne, hit the like button and subscribe. And tell me in the comments, could you handle seeing 2 different images with your eyes, or would your brain just quit? Thanks for watching.